Now let us solve the second tutorial problem. This is 5.19. So in this case, we have a batch process which is often used in chemical and pharmaceutical operations to achieve a desired chemical composition for the final product. It typically involves transient heating operation to take the product from room temperature to the desired process temperature at which the reactions etc. can occur. Okay. In this case, you have a chemical for which the density, specific heat, and the volume it occupies is given. You can also see this figure here. So you have to heat this chemical, you have these coiled tube. This coiled tube passes steam at 500 Kelvin, and this coiled tube has thin walls, and the diameter of the tube is 20 millimeters. Okay, the initial temperature of the chemical is 300 Kelvin. So the chemical initially is at room temperature, but you want to take it to 450 Kelvin. So the whole reason you have this tubing inside this chemical is to take it from 300 Kelvins to 450 Kelvins. And what's given to us is the heat transfer coefficient for the inside, because you have steam flowing in the tube. So since steam can condense and give a large amount of heat, so the heat transfer coefficient associated in this with this is 10,000 watts per meter square Kelvin. As we know, condensation heat transfer and boiling heat transfers are really high. And then the outside heat transfer coefficient, which is the outside heat transfer coefficient, which is between the pipe and the liquid out, the chemical outside, is 2000 watts per meter square Kelvin. So in this case, we are required to heat this chemical from 300 to 450 kelvins in 60 minutes. Okay, so we have 1 hour to heat this whole chemical. Given the volume of the chemical and all the thermophysical properties of the chemical, we have to find the length of the tubing that is required to achieve this amount of energy transfer. Okay, so let's solve this problem. So this is 5.19. So in this case, we will assume, so what we see here is that at the bottom we have a fan. So this fan ensures that the chemical that we have here is well mixed. So when you mix the chemical really well, it results in a homogeneous, almost a homogeneous distribution of temperature. So what we can say is that this temperature only depends on time. It does not depend on space, because the chemical is well mixed using this fan. And this mixing also ensures that the heat transfer coefficient between the pipe and the chemical on the outside, the pipe and the chemical is really high, because this mixing, as we know that increased mixing results in increased heat transfer coefficients. Okay, so since the temperature only is a function of time, and the initial temperature is given to us, so Ti is 300 Kelvin, we can use the lumped capacitance analysis. So if I write the result for the lumped capacitance analysis, it says theta upon theta I is exponential of minus T upon tau, or minus T upon R thermal times the capacitance. Okay, a theta in this case is given as temperature minus T infinity. So the T infinity is the max temperature it can attain, and that temperature in this case is 500 Kelvin, because T for steam is 500 Kelvin. So it's a high pressure steam, so it's 500 Kelvin. Uh, well, it could be atmospheric as well. So you have steam at high temperature. So that's your T infinity. Okay, because there's this chemical at max can go to T infinity. And in the denominator we have Ti minus T infinity. Okay, that is what theta I is. So theta can starts with T equals Ti. So that means theta is equal. Well, this whole thing is let's say theta star. So the theta star is equal to 1 initially, and then at after a long time this tends to 0 because T tends to T infinity. We're talking about a lumped capacitance analysis, so this is exponential of minus T upon the resistance is the resistance because of convection, because the heat transfer is happening to the chemical due to convection. And in this case the convection is happening first from the steam to the outside, so the steam to the inside surface, so and then from the inside to the outside surface. So we will simply say that the resistance is 1 upon the net heat transfer coefficient times the surface area, and the capacitance is rho times V, which is the total volume times the Cp. So this can be written as HA upon rho Vc times T with a minus sign. Okay. Now in this case the temperature T infinity is known. T initial is 300 kelvins as given to us, and the the temperature at some time T is also known. So this is 450 kelvins. Because you want this temperature to be 450 Kelvin, so that means you can obtain this time T, because everything else is also given. So the H in this case, the net resistance has to be, the total resistance has to be added. So if I take the two resistances, so one is 1 upon H inside times A, plus the other is 1 upon H outside times A, and that net is 1 by HA. So 1 by H becomes 1 upon HI plus 1 upon HO. Okay. So I can write this 1 by H as the sum of 1 by HI and 1 by HO. So this H is also known. The area is the total surface area. So that total surface area is given as the circumference, which is pi d, times the length of the tubing. So this is where the length of the tubing comes into the picture. More the length, more the surface area for the transfer of heat through convection. The density of the chemical is known. Total volume of the chemical is also known. That's given to us, and the specific heat is also given to us. So we can, I won't solve it, but we can solve this equation for the time T. Well, actually, sorry, we're not solving for T. Time is also given to us. Time is given as 60 minutes. Okay, so this time is also given. So what we have to solve for is A, because the length L is not given. Okay, so once we solve this using the value of T as 60 minutes, this will give us the value of A, and from A we can then calculate the value of L. Okay. So again, I will leave it to you to do the calculations, but it should not be too much of a problem given this formula.